We've been discussing the periodic table and trends in the various groups of elements. So today we're going to be taking a look at elements in group 2 and trying to determine what the trend is in reactivity as we go either up or down the group. Different groups on the periodic table will exhibit different trends. In some groups, as you go down the group, the elements become more reactive. In some groups, as you go down the group, they become less reactive. So your task today will be to determine what the case is for group 2. In part A of the lab, we're going to be looking at magnesium and calcium, two of the members of the group 2 elements. And we're going to be trying to do two things. First of all, we're going to determine what of these two elements is the more reactive. Secondly, we also want to react them with hydrochloric acid to produce magnesium and calcium chloride, which we're going to use in the second part of the experiment. So in the first part of the experiment, we're going to be weighing out a small amount of magnesium and calcium in 2 beakers, and then adding to that some hydrochloric acid. You'll want to observe what happens in the reaction because one of your tasks is to determine which of the two metals is the more reactive, so we can get an idea whether the reactivity is increasing or decreasing as we go down the group. We want to save those two solutions because we're going to use the magnesium and calcium chloride that we prepared in part B of the lab. Now the other goal of part A is to determine which metal is more reactive, magnesium or calcium, and as you're going to find out, when you use hydrochloric acid, it's going to be difficult to tell the difference. Hydrochloric acid is a pretty powerful chemical, and a lot of things react very vigorously with that. So we're going to do a second pair of experiments in part A, where we're going to take 2 test tubes, and we will fill them each about half full of deionized water, and then put a piece of calcium in one test tube and a piece of magnesium in the other. Water, of course, is not an extremely reactive material, and only one of those metals is actually going to react with it. So when you answer the question, which of the metals is more reactive, calcium or magnesium, you want to base that conclusion on what happened in the water, not the hydrochloric acid. In part B of the lab, we're going to carry out a series of 20 reactions. So we're going to look at reactions of magnesium, calcium, strontium, and barium with 5 different reagents and look at each of those four metals and see how their reactivity changes with these various substances. And in the end, you're going to come up with trends. You're going to look at each of the elements in the group and determine what the trend is. Do they become more reactive? Do they become less reactive? I have written a pre-lab which will go into much more detail. This is just an introduction, so be sure and read the pre-lab, which will talk in more detail about how to analyze the data that you collect, and then we'll head on over into the lab and carry out these reactions. We're going to be studying the properties of elements in group 2, and we call them periodic properties because they repeat periodically. In fact, that's why, of course, we call it the periodic table. Now, there were other scientists before Mendeleev that had this idea that properties in the elements could be predictable, that they weren't just random. Back in 1815, a German chemist by the name of Johann Dobereiner came up with something called the law of triads. He noticed that certain trios of elements had similar properties. For example, lithium, sodium, potassium, or calcium, strontium, and barium. He also noticed that if he arranged those triads of elements according to their atomic weight from the lightest to the heaviest, that the properties would change according to atomic weight. Sometimes the properties became greater, sometimes lesser. As you would go, say, from lithium to sodium to potassium, we find that the density of the elements decreases. He also noticed that if you looked at the properties of the lightest and the heaviest element in a triad, that the properties of the element of the intermediate mass would essentially be an average of those. So he was the first one that had this idea that there was some predictability in these elements. If you knew something about two of the elements, you could make a prediction about the third. In some groups of elements, we find that they become more reactive as their atomic weight increases, and in some groups of elements, it's the opposite. So let's take a look at a little video here that examines the elements in group 1, not only lithium, sodium, and potassium, but it goes all the way down group 1, and let's see if you can figure out what the trend is in reactivity as we go down that group. After this first video, take a look at this one from 1947. You can tell that there weren't a lot of safety regulations back in those days. But you saw earlier maybe a fraction of a gram of sodium. Now watch what happens when over a ton of sodium is tossed into water.
Pounds of highly dangerous metallic sodium head for destruction in Lake Lenoir, Washington. The government surplus chemical ignites and explodes when wet. The alkali lake is devoid of fish and forms an admirable disposal spot. A 3,500-pound container of sodium hurtles into the lake and crashes through a foot of ice. As the water seeps in, smoke rises through a series of muffled explosions. The acrid clouds billow several thousand feet over the steep sides of the lake. Disposal of the chemical by the War Assets Administration is made necessary because no public carrier will accept it for transportation to a purchaser. One after another, with varying effects, the containers go up with spectacular results as water and sodium meet. A once lethal war chemical becomes a peacetime pyrotechnic display.
Well, I hope you enjoyed those videos. I never get tired of watching those explosions. So let's go ahead and move on now. Later in the mid-1860s, an English chemist by the name of John Newlands came up with another observation regarding the elements. He looked at the elements listed in order of increasing atomic weight, just as Dobereiner had done. And he noticed that if he put them in order, at least of the known elements, he found a repeating pattern that every eighth element seemed to have similar properties to the first one in the series. And he realized that that was the same type of thing that occurred in music in octaves, that every eighth note is essentially a repeat of the first one. So he came up with this law of octaves, which seemed like a pretty clever idea, but unfortunately he got no acceptance. The British Chemistry Society saw no benefits to his discovery, and for many years he was basically a laughingstock. But eventually people realized that he had actually made a good discovery, and he became a member of the Royal Society. It was only a few years later that Mendeleev finally came up with a periodic table that people believed to be useful. He sort of put together the ideas of both Newlands and Dobereiner. Dobereiner had found that elements in a group tended to have similar properties. So going up and down these groups, we found properties were similar. And Newlands found that as you went across the table in order of increasing atomic weight, the properties tended to repeat themselves as you went across. Mendeleev's first table was fairly crude, but eventually it led to our more modern table here, where we have our vertical groups numbered from 1 on to 18, and then we have our horizontal periods, thus the periodic table. So today we're going to be studying the elements in group 2, and we want to see what kind of trends there are, because if there's one thing that all those chemists found is that there are trends or patterns in the properties of these elements. And we're going to study the elements in group 2, specifically magnesium, calcium, strontium, and barium, and see what trends we can observe. And the important thing to keep in mind is a trend allows you to make predictions. So I don't want you to just tell me what you observed in each of the reactions today. I want you to tell me what it means. For example, I mentioned a little while ago that as you go from lithium to sodium to potassium, the density of the elements decreases. So based on that, what would you predict about the density of rubidium? And logically, the trend appears to be a decrease in density as you go down the group. We would expect rubidium's density then to be even less than that of potassium. In part A of today's experiment, we're going to be looking at reactions of magnesium and calcium metal, and we basically have two goals. Number one, we want to determine which of those two elements is more reactive, and number two, we want to prepare a compound of each magnesium and calcium that we can use in part B of the experiment. So our first reaction will be magnesium and hydrochloric acid, which is going to make magnesium chloride and hydrogen. We'll then do a second similar reaction with calcium, which will make calcium chloride and hydrogen. Now you probably noticed that these reactions look very similar. Both magnesium and calcium have two chlorides, and in each case, two molecules of hydrochloric acid are required. That shouldn't be too surprising because the fact that magnesium and calcium are in the same group, we would expect their reactions to be similar to one another. The first question at the end of the experiment asks you for evidence that a chemical reaction has occurred in the reactions of magnesium and calcium with hydrochloric acid. So what kind of things tell us that a chemical change or a chemical reaction has happened? There are several common ones. One of the most common, of course, is a change in color. A color change is invariably a chemical change. Color is dependent upon the structure of a compound, so if the color changes, that means the structure of the compound has changed and you've made something new. Formation of a gas is normally an indicator of a chemical reaction, as is the formation of a solid, which is also called precipitation. We're going to see quite a few precipitation reactions in the lab today. Two very common things is a change in smell and a change in taste. If you're cooking a steak on the grill, you notice that it changes color, it smells different, it tastes different. All of those indicate that you have had a chemical change or a chemical reaction occur. Now, the second part of the second question at the end of the lab is to determine which of these two elements was more reactive. The problem with hydrochloric acid is that it's a very reactive substance, and so both magnesium and calcium are going to react quite vigorously with the hydrochloric acid. So we're going to have to do something more to try to determine which of them is truly the more reactive element. At the end of this part of the reaction, all you can say is they're both very reactive. So what we're going to do is we're going to carry out a second pair of reactions, but instead of hydrochloric acid, we're going to use water. Water is not a very reactive substance. If that were the case and you drank it, it would probably burn you. So water is a pretty inert material. Only the most reactive substances will actually react with water. So we're going to carry out one reaction between magnesium and water and a second reaction between calcium and water. I can tell you this much, only one of those two is going to react with the water, and that should make it very obvious to you which one is the more reactive element, and then it also asks you if there appears to be a trend in the reactivity, and the results of those two reactions should allow you to come up with a trend. In Part B, we're going to be examining this idea of trends in more detail. We're going to be looking at reactions of magnesium, calcium, strontium, and barium chloride with four different chemicals: sodium carbonate, sodium hydroxide, sodium sulfate, and potassium chromate. What you'll want to do is, after each of these reactions, observe what happens and then look at the reactions down the group and see if there's a trend or a pattern. I can tell you, of course, there should be. You should be able to observe a trend of either an increase in reactivity or a decrease in reactivity as you go down the group. In some groups, as you go down the group, the chemicals become more reactive. In some cases, it's less. It will be your job to figure out today which is which. Now, you might be wondering why hydrochloric acid is in this column. Hydrogen and chlorine are not members of the group 2 elements. The hydrochloric acid in this case is our control group. Remember that we made magnesium chloride and calcium chloride in Part A. The other chemicals, these 3 and the 4 across the top, are all provided for you, but we're going to use the magnesium and calcium chloride that we made in the lab. The problem is the magnesium and calcium chloride also contain unreacted hydrochloric acid that we used to prepare them in the first place. So let's consider a hypothetical reaction. Suppose we mixed our magnesium chloride solution with the sodium carbonate and it turned purple. Can we conclude then that magnesium chloride reacted with sodium carbonate? And the answer is no, because there's also leftover hydrochloric acid. Isn't it possible that it was the hydrochloric acid that actually reacted and caused it to turn purple? The one way we can check that is to test hydrochloric acid by itself. This hydrochloric acid will be our control group here. So let's suppose we mix the hydrochloric acid by itself with sodium carbonate, and it also turned purple. What is our conclusion? Well, of course, that tells us that it was truly the hydrochloric acid that reacted with the sodium carbonate and not the magnesium chloride. So our final conclusion would be that magnesium chloride did not react with sodium carbonate. On the other hand, suppose we added the hydrochloric acid to the sodium carbonate and there was no reaction. In that case, that purple color must have been caused by the magnesium chloride, and thus we can assume that magnesium chloride did indeed react with the sodium carbonate. Question number 3 at the end of the lab is based on the observations you make here with the hydrochloric acid and the magnesium and calcium. It simply asks if any of the reactions that you observed with the calcium and magnesium could have been caused by the hydrochloric acid. So by comparing what happened with the magnesium and the calcium to what happened with the hydrochloric acid, you should be able to answer that question. Now, one thing I should point out, I've had students many times over the years get really nervous when we do the experiment and nothing turns purple. Nothing's going to turn purple. I used purple as an example because I didn't want to give away what was actually going to happen. I can tell you that you will see precipitation, you will see bubbles, you will see color changes in various of these 20 reactions. Now, the final question in the lab, question number 4, asks you to identify trends in each of these 4 columns. So looking at the magnesium, calcium, strontium, and barium with each of these 4 chemicals. So there's question 4 has a part A, B, C, and D for each of these compounds. The question says, were there any trends in the reactivity of the elements? Where students commonly get that question wrong is instead of telling me what the trend was, they simply tell me what they observed. They'll say, oh, magnesium did this, calcium did this, strontium did this, and barium did this. That's not a trend. What I want you to do is to look at those series of 4 reactions and tell me, was the amount of reactivity increasing? Was it decreasing? That's what a trend is. If you've truly identified a trend, you should be able to predict what other elements in the group would do as well. For example, beryllium chloride would be above magnesium, and radium chloride would be below barium. If you've correctly identified the trend in the column, you should be able to extend that to predict what's going to happen with the element above magnesium and the element below barium. That's what made Mendeleev's periodic table so useful, is that people were able to predict the properties of elements that they had never studied or perhaps hadn't even been discovered yet. So this should give you all the information you need. I'm going to now head into the lab and we'll do each of these 20 reactions. I want you to observe all 20 of those and then write down your observations, and then you can use those observations to answer questions 3 and 4. All right, let's begin part A by weighing out a piece of calcium and magnesium. We want to weigh out about 1/10 of a gram of each of those to dissolve in hydrochloric acid. To make it easy, we'll just use the tare function on the balance. That will remove the mass of the beaker, and now we can weigh the magnesium directly. So we'll add a piece of magnesium, and it looks like that's pretty close to 1/10 of a gram, so that should be fine. It doesn't have to be exactly that, just in the ballpark. We'll go ahead and weigh a second beaker and tare that one as well. And then we'll add about 1/10 of a gram of calcium. And that looks pretty close. So we should be good to go. For the first part of the experiment, we're going to add about 10 milliliters of our dilute hydrochloric acid to each of our two beakers, the one with the calcium and the one with the magnesium. It doesn't have to be exactly 10, so we'll do it approximately. And it looks like we're getting quite a vigorous reaction there. So it looks like both calcium and magnesium react quite vigorously with hydrochloric acid. That reaction is already done. And now we've prepared our solutions of magnesium and calcium chloride. There's two parts of this experiment. In the first part, we're going to simply be preparing solutions of the calcium chloride and magnesium chloride to use in part B. And the other goal is to determine what's more reactive, calcium or magnesium. So to do that, we're going to carry out a second experiment, but this time we're going to use water instead of hydrochloric acid. So let's go ahead and add some water to each of these two test tubes. And now to one test tube, we're going to add a piece of magnesium, and to the other test tube, we'll add a piece of calcium. So we'll get ourselves a piece of magnesium here, and put that in one of our test tubes. There we go, there's our magnesium. And now let's add a piece of calcium to the other test tube. And let's observe what happens. It's pretty obvious in this case that the calcium is very reactive in water, but the magnesium is basically doing nothing. So based on these results, we can conclude that calcium is definitely more reactive than magnesium. In the hydrochloric acid, both of them appeared to be equally reactive because hydrochloric acid is a very powerful substance, but in water, the calcium clearly reacted quite vigorously, while the magnesium is not reacting at all. For our first series of reactions in part B, we're going to combine sodium carbonate with magnesium, calcium, strontium, and barium chloride to see if there's a trend going down the group. So let's first add some of our sodium carbonate. And now let's add to that some of the magnesium chloride solution we just prepared in the lab. Oh, and you can see it's quite vigorous bubbling there. So clearly there's a reaction taking place between those two. The question is it reacting with the magnesium or is it reacting with the excess hydrochloric acid left in the beaker? Next, let's look at the reaction between sodium carbonate and calcium chloride. So again, we'll add some of the sodium carbonate to our test tube. And now we'll add some of the calcium chloride. Oh, and like the magnesium, we got a significant amount of bubbling there. So clearly a reaction again this time. The next reaction will be between sodium carbonate and strontium chloride. there's some of our sodium carbonate. And we'll add some strontium chloride to that. And we see a very quick reaction between the two. This time, instead of bubbles, we're getting a cloudy precipitate. And this will be the reaction between sodium carbonate and barium chloride. So there's our sodium carbonate. We'll add some barium chloride to this. And we get a very dense precipitate this time. As we mentioned in the pre-lab, the reactions we saw with magnesium and calcium could have been caused by the excess hydrochloric acid that we had in our first two beakers. So to test that and be sure that wasn't the case, we're going to carry out a reaction between sodium carbonate and hydrochloric acid directly. If the hydrochloric acid also forms bubbles, then we can assume that it was the hydrochloric acid and not the magnesium and calcium that was responsible. If not, if there are no bubbles, then it was indeed the magnesium and calcium. But clearly, we got some significant bubbling there as soon as we added the hydrochloric acid. Here's a view of all 5 of the reactions with sodium carbonate. The bubbles in the first, second, and last test tube have pretty much dissipated, but you saw in the video what happened there. And the precipitates in the third and fourth test tubes are still quite obvious. Our next series of reactions will be with sodium hydroxide, again with the magnesium, calcium, strontium, and barium, and then our test hydrochloric acid sample. So let's go ahead and add some sodium hydroxide. And we'll add to that some of our magnesium chloride. Okay, doesn't seem to be any sign of a reaction taking place. No bubbles, no precipitate, no color change. Next, we'll combine sodium hydroxide with calcium chloride. So there's our sodium hydroxide. And we'll add to that some calcium chloride. And once again, it doesn't appear that any changes have taken place. Next up, we'll have sodium hydroxide and strontium chloride. So there's our sodium hydroxide. And some strontium chloride. Once again, it doesn't look like a lot is happening. It's getting a little bit cloudy. Oh, there we go. Now we're seeing some precipitate forming. It's a fairly light precipitate, but it's definitely turning cloudy. So this time there was indeed a reaction. It's getting cloudier and cloudier. It's just taking a little bit of time. And this will be our reaction between sodium hydroxide and barium chloride. So there's our sodium hydroxide. And we'll add to that some barium chloride. Oh, and it became cloudy much more rapidly this time. Seemed to react much more quickly than the strontium chloride did. And finally, let's run our control sample of sodium hydroxide and hydrochloric acid. So there's our sodium hydroxide. And we'll add some hydrochloric acid to that. And it appears that no reaction occurred here as well. And here are all 5 of the reactions with sodium hydroxide. The first 2 with magnesium and calcium appear to have no reaction, and the same occurred with the hydrochloric acid by itself, but we did get a precipitate with the strontium and barium. Our third series of reactions will be with sodium sulfate and each of the elements from group 2. So let's go ahead and add some sodium sulfate to our first test tube. And then we'll add to that some of our magnesium chloride. And it doesn't appear that any change occurred. Now we'll carry out the reaction between sodium sulfate and calcium chloride. So there is some sodium sulfate. And we'll add some calcium chloride. And once again, it doesn't appear that anything is taking place. Now we'll try sodium sulfate and strontium chloride. There's some sodium sulfate and some strontium chloride. And this one doesn't seem to be reacting at first. Oh, there we go. It's starting to get a little bit cloudy. So just a bit slow with strontium as it was in the previous one, but now it's definitely forming a precipitate. Next, we'll combine sodium sulfate and barium chloride. So there's our sodium sulfate and some barium chloride. Oh, we got a very rapid precipitate that time. Barium clearly reacted very quickly. And finally, let's try the sodium sulfate with the hydrochloric acid by itself. So there's our sodium sulfate and some hydrochloric acid. And it appears that there was no reaction. Here are all 5 of the reactions with the sodium sulfate, and like the sodium hydroxide, the magnesium and calcium showed no reaction, as did the hydrochloric acid, but both the strontium and barium formed a precipitate. For our last series of reactions, we will be using potassium chromate. So we'll add some potassium chromate to our test tube. And then we'll add to that some of our magnesium chloride solution. Ooh, that's a very pretty reaction that time. Turned a lovely orange color. The question, of course, is, was that because of the magnesium, or was that because of the excess hydrochloric acid? And this reaction will be the potassium chromate with calcium chloride. So there's our potassium chromate and a little bit of calcium chloride. We got that lovely orange color again, which may or may not be due to the calcium, might be due to the hydrochloric acid. Our third reaction will be potassium chromate and strontium chloride. So there's our potassium chromate. Add to that some strontium chloride. And it doesn't appear that any reaction is taking place. No color change, no precipitate. And number 4 will be the potassium chromate and barium chloride. So there's our potassium chromate and some barium chloride. And that time we got a very nice precipitate. Clearly there was a reaction in this case. Finally, let's take a look at potassium chromate with hydrochloric acid to see whether or not it was responsible for that orange color we saw with the magnesium and calcium. And it appears that it definitely was the cause. And finally, here is all of the reactions that took place with the potassium chromate. The magnesium, calcium, and hydrochloric acid all turned at a lovely orange color. Strontium seems to have remained unchanged, and barium formed a precipitate. So this is all the information you should need to complete the lab. You can go ahead and answer all the questions and then submit your experiment.